In this video, we are going to look at how to calculate the lambda max, or the maximum wavelength of absorption of a particular compound as proposed by the Woodward-Fierser. So these two scientists proposed a theory which can be used to predict or calculate the maximum wavelength of absorption of a particular compound. So they were called Woodward-Fierser rule. So we have the name as Woodward. So we have Woodward-Fierser rule. These two scientists came together to propose a theory which can help to predict the maximum wavelength or the lambda max of absorption of a particular compound. Now, before then, let's look at some terminologies which are used in calculating the lambda max of a compound. Let's first look at a term we call a diene. So when we say a diene, what is a diene? Now, what is a diene? 1,3-beta diene is a conjugated system which is made of two double bonds flanked, or let's say alternated by a single bond. So this is called a diene. That is 1,3-beta diene. That is the first term that we are going to look at. We are going to look at also what is meant by a cis diene and a trans diene. So a cis diene is a diene in which the double bonds are at the same side. So this is a cis diene. That is a diene that has a double bond at the same time or at the same side. Then we have what we call a trans diene. A trans diene. So this is a cis diene where we have the double bond at the same side of a single bond. Then we have a trans diene. So this is a trans diene where we have the double bonds between, or let's say at opposite sides of the single bond. So we have one shown down here, then the one shown up. So if you have the two double bonds at opposite sides of the single bond, we call it a trans diene. If you have it at the same side of the double bond, that is they all showing up or showing down, we call it a cis diene. Now let's also look at what we call a homoannular diene. The homoannular diene. So this is a homoannular diene. A diene in a ring system. When we say an annular means what? A ring. A ring. So a diene in a ring system where all the double bonds are found in the same ring is called a homoannular diene. So this is a homoannular diene. So when you have a diene in the same ring, we call it a homoannular diene. We have what we call also a heteroannular diene. A heteroannular diene, that is a diene that has the double bonds in different rings. So this is a heteroannular diene. A heteroannular diene. We have two fused rings, but other ones are found in different rings. So one is found here, then the other is what found here. So this is a conjugated system. That is, it is having an alternating single and double bond. So this is a heteroannular diene. So we have the dienes, or the two double bonds in different rings. So heteroannular diene. Heteroannular diene. We have the two bonds at different or in different rings. It's called a heteroannular diene. The next term is what we call an exocyclic double bond. As the name implies, exocyclic double bond. What is an exocyclic double bond? So an exocyclic double bond is a double bond which is just fused to a ring system. So when I have, let's say, this compound, and I have a double bond here which is fused to this ring system, I call this double bond an exocyclic double bond. So let's say I have a two ring fused together like this, and let's say I have this double bond here and another double bond here. If here is ring A and here is ring B, then I will say this double bond here is exocyclic to ring A, then this double bond here is exocyclic to ring B. So an exocyclic double bond is a double bond which is fused to a ring system. This compound has a typical one exocyclic double bond. Let's see if I have this compound too. If I have such a system, if I have such compound, Let's say I have this. This compound has just one exocyclic double bond. This double bond here is exocyclic to this ring. So the double bond that is fused to a ring directly, that's bonded to a carbon in a ring system, is called an exocyclic double bond. An exocyclic double bond. Next, we are going to look at what is meant by a double bond extension conjugation. Double bond extension conjugation. So when we say a double bond extension conjugation, when I have, let's say, this ring system, let's say I have this diene with double bonds, and I extend again with another double bond. I call this third double bond a double bond extending conjugation because I have a diene and it has been extended by one other double bond. So it's called a double bond extended conjugation. I have a ring system. If I have such ring systems, I have this and another ring fused to it. If I have a double bond here and this one, these two are cissoid or cis to each other. If there's another double bond here, then this double bond here becomes a double bond extending conjugation to the cis structure. So this one becomes an extending conjugation of the two diene or the diene here. So when we increase the double bond of a diene, we have a double bond extending conjugation. The next one is what we call an acyl substituent. An acyl substituent. When I have a diene like this, and any of the hydrogens here in this system that I can see is replaced by a carbon, I will call it an acyl substituent. So let's say if I have this compound, then the hydrogen here is replaced by, let's say, an acyl group. I call it an acyl substituent. If I have the hydrogens here replaced by an acyl group, I will call it an acyl substituent. If I have the hydrogen here replaced by acyl group, I will call it an acyl substituent. If I have the ones here replaced by an acyl group, I'll call it an acyl substituent. The acyl substituent is the same as a ring residue when it finds itself in a ring. So let's say in this compound, I have such a compound with two double bonds. So let's say I have this and that. So this is a template, the template diene. The ones here is a template diene. The acyl substituent of this is the same as the ring residue. If the acyl group is in a ring, I'll call that acyl group a ring residue. So here, the acyl group which replaces the hydrogen here is this acyl group. It's also called a ring residue. This one too is a ring residue which has replaced the hydrogen at this position of the diene. The one here too is a ring residue which is just the same as what the acyl group. So the acyl group and the ring residue are basically the same. The only difference is that with the ring residue, the acyl is forming or is part of the ring system. The acyl is part of the ring system. So these are some basic terms that we have to understand before we can go ahead to calculate the lambda mass of a particular unknown compound. Now bear in mind, in UV spectroscopy, the portion of the compound where absorption occurs is what we call the chromophore. So the chromophores are basically the conjugated systems that are filled with electrons where there can be an excitation of electrons for us to observe the spectrum at a particular wavelength. Some substituents, which we call oxochromes, increase the wavelength of the absorption. Others too may decrease, but most of the times they tend to increase the wavelength of absorption through a term called batochromic shifts. And these substances are called oxochrome, and they tend to increase the wavelength of absorption by a factor which is unique to a particular compound, or let's say a particular substituent or functional group. Let's see how we can predict the wavelength of absorption when we add an oxochrome to a chromophore. That is what is predicted by the Woodward-Fierser rule. So let's see. Okay. So these are the chromophores which can add it to a particular compound or residue. of a known wavelength or a known base value wavelength, they may alter the wavelength of absorption. So if I have a diene, let's say if I have a diene with a base wavelength of absorption of, let's say, normally when you have a trans system, it is always 217 nanometers. This is the base value of absorption of a diene. When you have it in a ring form, that is a cissoid form, it absorbs as 253. These ones are the base value. The base value. When you have even it in an acyclic form as a cissoid, those absorbs at the same 253. Now these 253 are the base value of absorption. So when we add any of these substituents to such a system, like let's say if I add an metal group here, I expect a change in the wavelength of absorption. If I add, let's say, OH here, I expect a change in the wavelength of absorption. If I add, let's say, an alkoxy group here, I expect a change in the wavelength base value of absorption. So these ones are basically called oxochromes, though they are chromophoric because they alter the electron density of the compound of the base value, which may change the wavelength of absorption. So when we have a base value or a base diene like this, and we add an ester functional group, that one adds no wavelength. When we add an acyl group, so an acyl residue, so either an acyl group or a ring residue, we increase the wavelength by 5. When we see an exocyclic double bond, as we saw earlier, the wavelength changes by 5. When we add an ether, we add 6 nanometers to the wavelength. When we add any of the halogens as seen here, we add 10 nanometers to it. When we see a sulfur, we add 30 nanometers. When we see a double bond extending conjugation, this one, to the diene, we add plus 30 nanometers. If we're able to see a secondary amine, we add 60 nanometers. When we see a phenyl group bonded to the base diene, we add 6 nanometers. So all these compounds cause what we call a biochromic shift because they increase the wavelength of absorption of a particular compound. Now let's see how we can calculate the wavelength absorption of a particular compound. So say you have this compound. Let's start with this compound. Say we have a diene, a typical heteroannular diene that has, so let's say you have this, we have such compound, and let's say we have here, so we have that. What is the lambda max of absorption of this compound? Now the base value of such a trans system or a heteroannular diene is 214 nanometers. That is the base value of absorption of the heteroannular diene. We can see a ring residue or an acyl substituent. So here, this is a ring residue that has replaced one of the hydrogens of the diene. We can see another ring residue here, which has replaced the acyl group or the hydrogen of the diene. We can see another ring residue here. So all these ring residues or the acyl substituents will increase the absorption wavelength by 5. So since we have 3 of the ring residues, we are going to add what? Plus 15. So the wavelength of absorption of this compound is going to be 214, which is the base value of absorption of this compound, plus 15, which is the acyl substituent, nanometers. So that is going to give us 229 nanometers wavelength. What if we have this compound? So let's say we have this, a very similar compound. Let's say we have this, then we have that, we have this, that, then we have that. how would the maximum wavelength of absorption look like for this compound? So in this system, we can see both a cis system and a trans system. So which one are you going to take as the base value? Well, when you have both cis and trans in the same compound, because the cis absorbs at a higher wavelength, we give priority to the cis conformation. So you are going to take the base value of the cissoid, which is the one in the first ring system. So the base value of the cissoid here is 253 nanometers. 253 nanometers. Then what can you see? We can see a double bond extension. So we can see plus 30. So this double bond here extends the conjugation. So we have extended this conjugation by 1. So we have one double bond extension conjugation. So we can have what? Plus 30. The next, we can see an exocyclic double bond. So an exocyclic double bond here. This double bond here is exocyclic to this ring. So if here's ring A and this ring B, this double bond is exocyclic to ring A. So we can see output plus 5. The next one is to look at for the acyl groups and the ring residues. The acyl groups and the ring residue. Now bear in mind, for the ring residues or the acyl group, we look at the ring residues or the acyl groups on all the double bonds present and not only the base value. So we look at the one on all the double bonds present and not only the base value. So we can see one acyl substituent here. We can see another acyl substituent here. We can see another acyl substituent or the ring residue here. So we have 3 ring residues or acyl groups bonded to the diene, or let's say bonded to the conjugations. So we can add what? Plus 15 to that. So we have 253. We have 253. 253 plus we have 30. Then we have 20. That gives us a value of 303 nanometers. That means this compound will absorb as 303 nanometer wavelength. Next, let's look at this compound. So let's say we have this. We have that. Then we have an extension here. Then we have this. So we have this. We have that. Then I think we also have this one. Then finally we have this. We have an acyl substituent here. How will the lambda max look for this compound? So we have first our base value. So our 6 compound, which is the second ring. Here's ring B, here's ring A, and this is ring C. So the ring B will have the 6 conformer, which will take our base value of absorption for this compound. So we have 253, which is the base value of absorption of a cis diene, that is a cis homoannular diene. 253 plus the next we have 2 double bond conjugations or extensions. So we have one. This double bond in the ring A extends toward the 6 conformer, and this one in the ring C also extends toward the 6 conformer. So we have 60 nanometers, which will be added by the 2 double bonds because each of them adds 30. The next one, we have one acyl substituent here. So this one acyl substituent, which adds 5 nanometers. We have another ring residue here. 2, we have another ring residue here. 3, we have another one. 4, we have 5, we have what? 6. So in all, we have 6 equal substituent or ring residues. That is what? 30 nanometers. We have 30 nanometers increment. The next one, we are going to look at the exocycle of bonds present. Now this one, this double bond is exocyclic to ring A. So we have one exocyclic with R5. This double bond is exocyclic to ring C. Then this double bond is exocyclic also to ring B. So we have 3 exocyclic double bonds. That will add up 15 nanometers. That's going to be plus 15. So we are going to get the total value of 253 plus we have 60 plus we have 30 plus we have 15. So we're going to get a total of 358 nanometer wavelength. 358 nanometer wavelength. Let's try a last question. Okay, so let's draw this compound. I think the space occupied, so let me clean the space. So we have, let me clean the space so we can have a white area for the new compound. So let's say we have this compound. We have this. This is a bit unique compound. Then we have that extension. Draw it well. So draw it a bit nicer. So I have that. Then I have that. So I have this compound. I have here an ester CA3. I have the double bond here. I have another double bond here. I have this double bond extension. I have this double bond extension. Then I have an alkyl group here. Then I have another alkyl group here. Now, what is the maximum wavelength of absorption of this compound? So we have 3 ring structures. We have ring A, we have ring B, and ring C. What is the maximum wavelength for absorption of this compound? So our base value is going to be taken from the ring B, which has a schizoid homoannular diene, which is what? 253 nanometers. 253 nanometers. The next one is our ring residues. So we are going to add from the ring residues. In the first place, we also have an ester. This ester, we said it has no wavelength, so we have plus 0 that extends from the double bond. Next, we are going to look at the ring residues that we have in this compound. So we don't only look at the base value, or let's say the base dienes ring residues, we look at the residues of all the double bonds of the conjugations present. So we have one here. That's our first ring residue, which can be observed. We have another one here, our second ring residue, which can be observed. So these ones have all replaced the hydrogen bonded to double bonds. We have the third one here, which is the next ring residue, which has replaced the hydrogen on the double bonds. We have our fourth one here, which has replaced a hydrogen on our double bonds. We have our fifth one here. So we have a total of 5 ring residues, or we can see 5 equal substituents. So that adds a total of 5 times 5, because each of them is 5. So we have 25 nanometer increment. 25 nanometer increment. The next one is our double bond conjugation. Now this is our base value, or our base double bond, that is the cis one. This double bond is an extended conjugation. Then this one too is an extended conjugation, each of which adds a total of 30 nanometers. So we're going to have plus 60 nanometers for double bond extended conjugation. Next, we are going to look at the exocyclic double bonds. The exocyclic double bonds present in this compound. So if I look very clearly, I can see that this double bond here is exocyclic to ring A. This double bond here is exocyclic to ring C. Then this one too is exocyclic to ring B. So we have 3 exocyclic double bonds. That adds a total of 15 nanometers, because each of them adds 5. So the maximum wavelength absorption of this compound is going to be 253 plus 25. 253 plus 25. So it plus 0. You can ignore the 0. Then plus 60. Then plus 15. So a total of 353 nanometer wavelength is going to be absorbed by this compound. 353. So we have 353 nanometers wavelength is going to be absorbed by this compound. So that's how you can just calculate the maximum wavelength, or lambda max, of absorption of a conjugated diene, as proposed by Woodward and Fierser. Thanks for watching. Don't forget to subscribe for watching, so you can receive all our updates from this channel. Thank you.